everybody. Nice to see you. I hope you're enjoying your day off. I thought I would maybe make another little video for you. So since we're missing our day where we're going to be going over the homework, and I could try to explain that a little bit more and maybe show you a few more things about what we were doing yesterday, because I got the sense at the end of yesterday's class that you guys were feeling a little shaky on the material, and I'm sure the homework was a little bit challenging. So I'll be sending you solutions. Hopefully you've received them already, and you can review those on the work that you did, and watching this video might actually help fill in the gaps of whatever you didn't understand. So first, let's just quickly review what we did yesterday. Remember that we always know for all waves that the velocity is equal to the frequency times the wavelength. That's our wave equation. And yesterday we were talking specifically about waves that travel along a string. And if you remember from the reading in the book and from some of the stuff that I said yesterday, standing waves, which are the kind of waves that we generated by shaking the string and making those waves that appear to just vibrate in place, really are formed because you generate a wave, that wave travels down and reflects off a boundary and it starts coming back, but meanwhile you start generating another wave, and if you shake it at just the right frequency so that the waves basically fit on the string, so that a whole number of half wavelengths fit on the string, you're going to wind up with something called a standing wave, where no matter how the waves overlap, they're either going to constructively or destructively interfere. And so the wave goes from being all in one direction to nothing when the two traveling and reflected waves are destructively interfering, to like being the other way, and we get all those little dances that we did yesterday. The straight up and down one, the half and half one, the middle up and the sides, and then the four one, and it can go on and on and on and on. So what I want you to know about standing waves, which we called, if you remember, do you remember what they're called? The harmonics of the string, or another way to say it, are the allowed vibrational modes of the string. I'll draw the first four on the board again, just as a review. Okay, the first four were when the string was just vibrating up and down. It was called the fundamental, or the fundamental frequency F1. There was the one where half of the string was going up and the other half was going down. That was F2, which was twice the fundamental. We had F3, which was where it was doing up in the middle and down on the sides, and then vice versa. And then finally, we drew F4, which, I should show that as, let me erase that. We had F4, which had the string going up and down and up and down in a more complicated way. And there's a 5 and a 6 and a 20 and a 30 and a 50 and a 10,000 also, but we're not going to draw all of them. So, and remember that every time we go to the next harmonic frequency of vibration of the string, we're going to increase the frequency by a whole multiple. So it goes from a certain frequency to twice that original, to 3 times that original, to 4 times that original. Okay, so if you want to have a little rule, the nth harmonic frequency, Fn, equals n times the fundamental frequency. So the third, it's 3 times the fundamental frequency. On the fourth, it's 4 times the fundamental frequency. Okay? And the thing to remember is that these are called standing waves. And those standing waves appear to be vibrating in place, but in your back of your mind, which no one ever really thinks about this when we look at standing waves, but in the back of your mind you've got to remember it's because there are waves traveling one way, hitting the boundary just the right way, so that the wave that's traveling back and the wave that's still coming down interfere in such a way that the wave string always stands in place. And I think I probably will have sent it by the time that you see this, or I will hopefully you'll watch it after this, though, an animation that shows how standing waves are set up, and that might help you if you're still feeling a little confused about that. Okay, so the quick thing I said at the end of class yesterday that was really poorly stated on my part was how we determine the velocity of waves traveling down a string. And if you guys remember, when we were out in the hallway a couple days ago last Friday, we took the big, long, golden, slinky spring thing, And we noticed that when it was pulled really tightly, the waves traveled really fast. They zipped down from one end to the other. When it was much looser, the waves seemed to travel down much more slowly. And so we started to get a sense that maybe the medium, the tension in the medium on the string might affect how quickly the waves actually travel. The other thing that we sort of said was that if a string is much heavier, it might take a longer time to shake and transmit the vibration. So we also guessed that maybe how massive or how dense the string is would actually determine the wave speed down the string. So what it turns out, and this was in your reading in the little sheet that I handed out to you guys for homework, that there is an expression that we can't derive because it takes too much fancy math to derive it, and I don't even think I know how to derive it. I'd have to probably figure it out. How to derive the velocity of waves as they travel down a string. And the velocity of waves on a string, so we'll call it v string, to remind ourselves that it's only the speed of waves that travel on a string, okay, is equal to the square root, and why there's a square root there is in the derivation that we're not going to do, times the tension. And I'll write tension instead of T so you don't get it confused with period, which is also capital T, which is a measure of how tight the string is. And like tighter strings would be faster wave speeds, that makes sense. And then also how heavy or dense the string is, and there's a quantity that measures that called linear density. And linear density is really a measure of the thickness and massiveness of a certain amount of the string. Its units, linear density, its units are kilograms per meter. So to figure it out, you basically take a certain length of string and weigh it, divide its mass by its length, and that's the linear density. Often you're given the linear density as kilograms per meter, so you don't have to do anything besides stick it in the equation. Sometimes you'll also be given a length of the string in the problem, but if you're given a linear density, you don't need to do any calculations. You just stick the linear density into that. So we'll do some examples like that in a little while. We'll go over the homework. So, for example, if you had a string that was, stretched to like 100 newtons of tension, and its linear density, these are typically small. Like those strings don't weigh a lot, right, normally. So maybe it's like 5 times 10 to the negative third kilograms per meter. Okay, if that happened to be the linear density, we could calculate, hopefully my calculator works. We would do the square root of 100 divided by 5e to the negative 3, and you get about 141 meters per second. So that's how you do that. And then you have the speed of the waves on this string. And even though these vibrations are all different, they're all different ways the same string is vibrating. So you can assume the string has a constant tension regardless of how it's vibrating, and that it has a constant linear density because you haven't changed the material properties of the string. So for all 4 of these vibrations on a given string, if it was tuned to that tension and that was at that linear density before I started plucking it and shaking it, this would be the speed for all 4 of these waves. Okay? So that's how that works. So one of the things you might have trouble with in the homework is, well, do the wave speed change as you change the string and as you shake it faster? And the answer is no. As long as the string is the same string, you haven't changed anything about it, you don't have to worry about the fact that the speed will always be the same because you can consider it a constant medium. And the speed of all waves, if you remember, is the same in all media. Okay? I'm going to go check my video right now to make sure it didn't stop.